Hey guys, I am Deric. Welcome to my channel. In this video, I'm gonna explain to you the special issues of capital budgeting. The first project ranking problem is about size disparity. Size disparity arises when we are dealing with mutually exclusive projects of unequal size. Unequal size implies that the cash flows for two projects are different. This is why the NPV decision may not agree with the IRR or PI. Our proposed solution is to select the project with the highest NPV. Let's look at the following example. Project A is a more costly project compared to Project B because its initial investment is higher, and you will receive more cash inflows from year 1 to year 3. Now let's look at Project B. It has a lower initial investment and lower cash inflows subsequently. As we mentioned, when comparing these two projects, they have size disparity problems. Based on a required return of 12%, Project A has a higher NPV, while Project B has a higher IRR, PI, and MIRR. For decision-making, we'll prefer Project A due to the higher NPV. A higher NPV means the project can generate more cash inflows for the company. Another problem in project ranking is the time disparity problem. It occurs when dealing with mutually exclusive projects that have different timing of cash flows. The projects may have similar sizes, but they receive cash inflows at different times. This discrepancy arises because NPV and PI assume that cash flows are reinvested at the required rate of return for the project. However, IRR assumes cash flows are reinvested at the IRR's rate. Consequently, NPV or PI decisions may not align with the IRR. Our proposed solution is to select the project with the highest NPV. Let's look at the following example. Project A and Project B have a similar initial investment size. Every year, the cash inflows are also more or less the same. However, the timing of cash inflows is different. Project B will receive more cash inflows in year 1 and year 2, whereas Project A will receive more cash inflows in year 3 and year 4. Based on a required return of 12%, Project A has a higher NPV, PI, and MIRR, while Project B has a higher IRR. For decision-making, we'll prefer Project A due to its higher NPV. A higher NPV implies that the project can generate more cash inflows for the company. Another special issue is about mutually exclusive investments with unequal lifespan. Suppose our firm is planning to expand and we have to select one of the two machines. They differ in terms of economic life and capacity. How do we decide which machine to select? As shown in this example. Machine 1 and Machine 2 have the same initial investment, which is CF0 equals $45,000. However, Machine 1 will receive $20,000 cash flow from year 1 to year 3, while Machine 2 will receive $12,000 cash flow from year 1 to year 6. To determine which machine is better, we'll need to calculate the NPV. Based on a 14% required return, the NPV for Machine 1 is $1,433, and for Machine 2, it's $1,664. So, does this mean that Machine 2 is better? No. In fact, the two NPVs cannot be compared because they have unequal lifespan. To address this problem, we'll utilize the equivalent annual annuity EAA method. If we assume that each project will be replaced by an infinite number of times in the future, we can convert each NPV to an annuity. That's the concept of EAA. Simply speaking, EAA is a single average cash flow for all periods that equals the project's NPV. To calculate the EAA mathematically, we may divide NPV by the PVIFA, which can be found in financial tables. Alternatively, you can use a financial calculator. As shown here, for Machine 1, key in the NPV is PV, negative 1,433, N equals 3, I equals 14, and then compute PMT, you'll get 617.24. By following the same method, you'll find that PMT equals 427.91 for Machine 2. This calculated PMT is in fact the EAA. The EAA for Machine 1 is $617, while the EAA for Machine 2 is $428. This information indicates that the NPV of Machine 1 is equivalent to an annuity of $617 per year, whereas the NPV of Machine 2 is equivalent to an annuity of $428 per year. By making this comparison, we can determine which investment is superior. In this way, we have simplified a problem with differing time horizons into a comparison of two annuities. The decision rule here is to select the machine with the highest EAA, which leads us to choose Machine 1. The replacement chain method is the second approach used to address the issue of unequal project lifespans. The rationale is quite straightforward: extend the project's lifespan to make both projects have equal lifespans, and then calculate the NPV. If the projects have no common lifespan, for example, 3 years versus 5 years, then extend the lifespans of both projects to 15 years. If the projects have a common lifespan, for example, 3 years versus 6 years, then extend the lifespan of the project with the shorter duration to match that of the project with the longer duration, which in this case is 6 years. Refer back to the same example, but this time we'll apply replacement chain method. Machine 1 has a cash inflow projection for 3 years, whereas Machine 2 has a projection for 6 years. To align the two projects with equal lifespans, we'll need to extend the lifespan of Machine 1 to 6 years. In simpler terms, in year 3, we'll need to reinvest $45,000. With an inflow of $20,000 and an additional investment of $45,000, the net cash flow for year 3 will be negative $25,000. Afterward, it will yield $20,000 every year from year 4 to year 6. Based on the extended cash flows for Machine 1, we can calculate the new NPV, which is equal to $2,400. When compared to the NPV for Machine 2, which is $1,664, we can conclude that Machine 1 should be selected. This is because the replacement chain associated with Machine 1 has a higher NPV than Machine 2. Alright, that's all for this video. Thanks for watching. See you in the next one. Bye.